Flying ice cube. In molecular dynamics MD simulations, the flying ice cube effect is an artifact in which the energy of high-frequency fundamental modes is drained into low-frequency modes, particularly into zero-frequency motions, such as overall translation and rotation of the system. The artifact derives its name from a particularly noticeable manifestation that arises in simulations of particles in vacuum, where the system being simulated acquires high linear momentum and experiences extremely damped internal motions, freezing the system into a single conformation reminiscent of an ice cube or other rigid body flying through space. The artifact is entirely a consequence of molecular dynamics algorithms and is wholly unphysical, since it violates the principle of equipartition of energy. Origin and avoidance. The flying ice cube artifact arises from repeated rescalings of the velocities of the particles in the simulation system. Velocity rescaling is a means of imposing a thermostat on the system by multiplying the velocities of a system's particles by a factor. These schemes fail when the rescaling is done to a kinetic energy distribution of an ensemble that is not invariant under microcanonical molecular dynamics. Thus, the Berenzon thermostat which rescales to the isokinetic ensemble exhibits the artifact, while the Bussy-Donadio Paranello thermostat which rescales to the canonical ensemble does not exhibit the artifact. Rescaling to an ensemble that is not invariant under microcanonical molecular dynamics results in a violation of the balance condition that is a requirement of Monte Carlo simulations molecular dynamics simulations, which is the artifact's underlying reason. When the flying ice cube problem was first found, the Bussy-Donadio Paranello thermostat had not yet been developed, and it was desired to continue using the Berenzon thermostat due to the efficiency with which velocity rescaling thermostats relax systems to desired temperatures. Thus, suggestions were given to avoid the flying ice cube effect under the Berenzon thermostat, such as periodically removing the center of mass motions and using a longer temperature coupling time. However, more recently it has been recommended that the better practice is to discontinue use of the Berenzon thermostat entirely in favor of the Bussy-Donadio Paranello thermostat, as it has been shown that the latter thermostat does not exhibit the flying ice cube effect. References